Okay, hello everyone and welcome to this video where we're going to look at the continuous random variable and their probability distributions. So this covers chapter 15. So let's jump straight in. We only have a couple exercises again for this chapter. As always, we're going to look first at what the continuous random variable is, have a look at its measures of center, so mean and median, then look at its measures of spread, and then use those in some form of applied questions effectively is what we're going to do. So let's just jump straight in. Exercise 13, we looked at discrete random variables. So that was when something was counted. Okay, so number of balls we get, number of students in the class, they're all exact numbers. That was the big thing about discrete. Well, continuous is continuous. They're not exact. They have decimal places that can technically go on and on forever. Now we know Usain's world record is 9.58 seconds, but that's actually rounded to 2 decimal places. If we had a more accurate measuring device where we could measure to an infinite amount of decimal places, the difference between continuous random variables can be infinitely small. So if we think we're getting to the millionth decimal place, so we've had like 0.19 or 0.18 have a million decimal places, and then we have 0.1, and then we have 0.18, another million decimal places, and 0.2. Those two are 2 different recordings. And we could technically have those decimal places go on for an infinite amount of places. Which means for a continuous variable, because you could have an infinite amount of accuracy, you can never say the probability of one exact thing happening is greater than 0. Because there's an infinite amount of options. So this is really weird to wrap your head around. But what I'm trying to say is the probability of any singular particular value. So if we said probability of 18.93, the probability of exactly 18.93 is actually equal to 0. Because you would have to measure to an infinite amount of accuracy, because technically that 0, 0, 0 is on and on forever, infinitely. And since you're going to an infinite amount of accuracy, you've got an infinite amount of options, which means it's effectively impossible to get exactly that. Long story short, even if you're a little bit lost with that, that's okay. We'll talk more about it in class. The big takeaway is if you're ever with a continuous variable, something that we're measuring to decimal places, if you're ever asked to find the probability of something exactly, so it's x equals, so we're not in a range, the answer is just going to be 0, is the big takeaway. So if the probabilities of being exactly some value is 0, then how are we going to use continuous random variables? Well, the way we use continuous random variables is we have to actually look in a range. We effectively have to use some form of histograms. Okay? So, if we make a histogram of the weights of people in a class or something, okay, again, we could, if we had enough accuracy in measuring devices, we could infinitely measure them. But what we could do, though, while we can't know exactly what their value is, we can know what band they would be in. So we can choose a number of decimal places to make a band. So we could make histograms that are to 0.5 bands. So in this case, we can see we're between 82.5 and 83.5. Now, we don't know if those people in there are 82.59992 or 9993 or 9994, but we know once we start rounding that they are going to be in that band. So we can put continuous measurements in bands. Okay. So that's going to be the big thing that we're going to always doing is we're going to define them over intervals or bands. We're going to stick them in. So we can have a look here. If we wanted to find the probability that the weight of someone is being equal to 83, what we're doing is we're actually saying, let's look at minus half plus half. We're going to put it in this band range. Now we could make that band 2 kilos wide, we could make it half kilo, we could make it 0.1 kilos wide. We get to self-select. But to actually calculate the probability of that is going to be, well, it's the number of successes. If we think of any form of probability, is going to be equal to the number of successes divided by total amount. Okay, and that's going to be the same as, well, that shaded area divided by the total shaded area, because that shaded area here in this band is going to be our number of successes, and then the total area is going to be the total amount of people surveyed. Because we would have, just start playing. This we could be as number of people. Now, this might be starting to ring a few bells. Area of bands, dividing things up into bands. We can make our bands as wide and small as we want. We have looked at that, and that's actually why we spent so much time in that topic. I've jumped ahead actually. I'm getting ahead of myself. Okay. This is just a continuation of what I was speaking on the last slide. The probability of being in a particular band is equal to the area of that band divided by total area. Now, the probability of the whole amount of outcomes can never be greater than 1. Okay, it actually has to be 1. It can't be less than 1, it has to be equal to 1. So the probability of being this band, we can simplify from our previous one. Instead of doing the shaded area in the band divided by the total area, we can simplify it because the total area, because sum of all probabilities, probability of all, has to always be equal to 1. So the area under that whole histogram is always going to be equal to 1. So we can now say the probability of our band is just equal to the area in that band. So it's a little bit of a simplification. And now where I was getting to at the end of the last slide when I was getting excited, areas under curves, bands, estimations. Instead of just doing an area of band, we can actually use integration to get a much more accurate solution. And we're not going to look at how to convert bands into this red curve. That's going to estimate those bands. That's for other subjects in almost university level. It's not too hard, especially with the CAS calculator, but it's outside the realm of this course. All we know is that what we're going to be given is we could be given bands, we could be given a histogram with bands, but what we are more likely to be given in this course is we're going to be told that this curve, okay, this function, if I could spell today, this function is an estimate, okay, or models the histogram. Okay. And it's a function that is modeling the probability and is telling us the density or expected amounts of values. So this is called a probability distribution function, or it's the continuous PDF. Okay, so we've looked at discrete, we've looked at binomial distribution, probability distribution functions. This is going to be the continuous probability distribution function. It is an equation of a line that gives us the best estimate of a histogram for a continuous value. Okay, it's telling us that maybe there's 3 people here, there's 4 people here, averages 4.5 there, 6, whatever it is, the values, but this curve could be a cubic, could be an exponential, could be a sine graph, whatever it is, okay? But we can use it to best estimate that histogram, and that is called a continuous probability distribution function. So a continuous random variable, to clarify, the random variable way back at the start, okay, is just measuring some event. It's a measure that can have decimal places. The continuous probability distribution function is a function that estimates probable outcomes. And we could get that by carrying out a few experiments or making some recordings, doing some maths to then give us this line of best fit. Rightio, so from that, and looking at all the other probability stuff we've done, there's a couple of things that we can draw out of this. Okay. The line or the value of the function, okay, the value of the function must be always greater than or equal to 0. That is saying that the line must always be over 0 because we can't have negative probabilities. Okay, as soon as we get, if this curve came down underneath the x-axis, we've now got some area under the graph. We know that as assigned area that's negative, that would be telling us we have a negative probability, which is impossible. Okay? So this first rule of a PDF is that all values must be greater than 0 or equal to or greater than 0 because we can't have negative probabilities. And the second one, okay, is that all probabilities must add up to 1. So the area under the graph must be equal to 1. So if we have a certain range, now this one may go to that axis there and it may actually end right there. Okay. If we say that's our whole area, okay, that means that that area in there, okay, needs to be equal to 1 for it to be a probability distribution function. Because if the area was greater than 1, then that's saying that if we summed up any band, or we summed up all the bands, doesn't matter how wide we decide to make them, if the area is greater than 1, then that's implying that the probabilities are greater than 1. Okay, so that's our two main rules. The line must always be above the x-axis, and the area must be equal to 1 for the total domain. Okay, so the total domain, so the total possible spread of values. And we write that for whatever the bounds are of our total domain, we can just write it here. The area under the curve must be equal to 1. That's all that is. We can go a bit further now from this. Okay? So before we talked about defining a certain band between like 1 decimal place, rounding 1 decimal place, 2 decimal places. What we can actually do now, because we've got a function, remembering this line is a function, okay, where the areas under it, okay, estimate. So what we really care about is the area under. The y value is effectively negligible for what we're doing. Okay, the y value itself isn't telling us the probability. It's the area under a certain region of the graph. Okay, so ignore reading off y values. That's going to lead you astray and really confuse you, as we need to purely think that the function is written in a certain way and has a certain shape, that it's the areas under it or the integrals for certain bands that are most important. What we can do, since that's how the function is defined, that's literally the definition of the function, is we can then look at any band we want. We might want to say, what is the probability between 30 and 45? And it might happen that 30 is there and 45 is there. And since the probability distribution function is defined as the area under it tells us the probability, we can just find the area under it for that range. We could find between 30 and 45, integrate, find the area, and that's now going to tell us the probability in that range between 30 and 35. A carry on from the idea that we could technically measure to an infinite amount of decimal places and that there can be no item that falls exactly on 30 or exactly on 45 means that if we have when we're defining our ranges, whether it be include one terminal or the other terminal or include both terminals, they are all actually going to be exactly the same value because the probability of 30 exactly is going to be equal to 0 and the probability of exactly 45 for a continuous variable is also going to be equal to 0. So including them, including those endpoints right on the line, makes no difference to when we're calculating our integral. Again, it's a little confusing, this idea of an infinite amount of decimal places and the probability of exactly being something is 0. The big takeaway is for continuous variables, it doesn't matter if it's including or not including. Just do the integration. That doesn't matter. Doesn't matter if it's not including, includes one, includes the other, or includes both. Just do the integration between that range and you'll be fine. last thing that we might see, it doesn't pop up as much in the exams anymore, okay, is, no, that's on the next slide. This slide is just another way of saying these two rules back here. The line must be always over, the line cannot be below the x-axis, and the total area must be equal to 1. This is a way of saying that mathematically, okay? The y values must always be equal to or greater than 0, and the total area from negative infinity to positive infinity, or whatever our outside terminals are, must be equal to 1. Total area must be equal to 1. That's just a way of saying it mathematically. Now, a lot of times, as we looked back at this graph though, the graph doesn't actually go on to negative infinity and positive infinity. It's actually going to have a set range. So we could have something that looks like this. Let's curve that up, and it's going to stop there. Okay. And this is going to be C, that's going to be D. And what this notation here is saying is that, yes, we have a function that estimates it between C and D, but outside that range, we're just going to say that our line is 0. It just stays on the axis. Since the y value is 0, that's what that's there saying, its value is 0, means there's no area under, which means there's no probability. And so then all this area here in the middle, that would have to be equal to 1. This is where I thought I was going to next slide, or previous slide. We could have the probability distribution function again, because we can have certain domains for it. We could define it as, say, 3 to infinity. Now, the integration we just calculated is from 3 to infinity, but the way it can be written sometimes is the limit as k approaches infinity. Instead of putting infinity, we put k up there. It's a little tedious notation, rarely ever pops up in the exam. It is just a way that probability distribution functions are written. All you have to do is look at the limit, okay, and apply the limit. Oh, it's as k gets to infinity, so I'm just putting infinity up where k is. Same down here, we could have the bottom bound is negative infinity. I need to put negative infinity in there. Or I could be going to negative to positive infinity. The function goes on and on forever in both directions. And we can have negative and positive infinity. But same thing, the area under all of those in total has to equal 1, because the total sum of probabilities can never be greater than 1. Right, okay. That's a lot of me talking. Let's get into applying. We're just going to look at one example, and then next class, in class, we'll do the final 2 examples. Let x be a continuous random variable with the following probability distribution function. So we've got some function, some equation of a line. It's k on x cubed between 3 and 6, and otherwise it is going to be 0. So we've got some function between 3 and 6 that has some curve, and then outside of that curve, it's 0. Okay. Determine the constant k such that f of x is a valid probability distribution function. Well, to be valid, that line here needs to be above the x-axis, so that's going to pretty much imply that k needs to be a positive value. And then second, we need to choose a k value so that the total area in that zone is equal to 1. Okay. So what we need to do is let the integral, so the area of k on x cubed dx, we need to let that equal to 1. Whatever the area is under that graph has to be equal to 1 for it to be valid. So we're going to integrate that, or actually let's change into polynomial form first to help. So we've got kx to the negative 3 dx is equal to 1, just using index laws. Now we can integrate, so this is going to become kx, add 1 to the power, so that's going to be negative 2 divided by the new power, negative 2, between the bands 6 and 3 is equal to 1. Do our substitutions, so we're going to get k, 6 to the negative 2 on negative 2, take away k 3 to the negative 2 on negative 2 is equal to 1. Let's come up here. Okay, we're going to get k on negative 2, 6 squared, take away k on negative 2, 3 squared is equal to 1. So we get k on negative 6 squared is 36 times by 2 is 72. Take away k on 3 squared is 9 times by 2 is 18. That's going to be negative there is equal to 1. 18, I bet we can multiply by something to turn into 72 to get common denominators. Is it going to be 4? Let's check. 4 8s are 32, 4 ones, yes, that's going to work. So this is going to become k on negative 72 plus, because I'm going to sort out these two negatives, 4k on 72 is equal to 1. So what we have is 4k on 72, take away k on 72, 1. 3k on 72 is 1. So k is going to equal 72 on 3, which is 24. Okay. And we're done. And this style of question is going to come up all the time in the exam. Or not all the time, it's almost guaranteed to come up in the exam. You're going to be given some equation, some function that estimates the probabilities. You're going to have to first figure out what the k is, and then once you've got the k, we're going to do a whole bunch of things that we're going to look at in the following exercises. Okay. Now, last thing that we can do, okay, is carry on, like I've said, is let's actually now use that. So we know that k is equal to 24, so our function f of x is now equal to 24 on x cubed, 0, and that's from 3. X 6, and that's effectively otherwise. Okay. Now we want to find what the probability of x being greater than 4. Now we don't know what context this is in. Okay, this could be, what's going to have low numbers like that? Amount of years spent in high school, or who knows what it is. Okay. It's something that we could measure. 2.8 years, whatever. But we want to know probability that x is greater than 4. If we think of what our graph is going to be, okay, it's going to have some shape to it, and I could graph it to know exactly what it is, but it's defined from 3 to 6. I want to know what the probability of greater than 4 is, so I'm effectively finding that. Now, the probability of x greater than 4 is technically equal to 4 to positive infinity of f of x dx, because it just says keep going on past 4. But since our function at 6 onwards is just 0, well, the area past 6 is just going to be 0. So what I could realize is that this is the same as 4 to 6 f of x dx plus from 6 to infinity of f of x dx, and since the value of the function greater than 6 is 0, well, that area is always going to be 0. So what I only need to find, instead of finding from 4 to infinity, I only need to find from 4 to 6 of 24 on x cubed dx. Okay. And we can do our integration. So that's going to become 24x to the negative 2 on negative 2 from 6 to 4. Let's come up here. Okay, because to integrate, I just added 1 to the power and divide by new power, and I've just taken the shortcut of changing the polynomial form first. So that's actually the same as negative 12 on x squared from 6 to 4. That's going to be negative 12 on 36, take away negative 12 on 16. That's going to be negative 12 on 36 plus 12 on 16. We could divide both of those. We could, no, hold on. Trying to find a common denominator. I turn 36 into 4. Divided by 9, that's 12. No. I can turn them both into 72, I'm pretty sure. No. Okay. Just to get this video over and done with, I'm just going to take the easy way out and put them into over 576. So 12 by 36 is 430. 432. 12 by 10 is 192. So 432. Take away 192. 240. On 576. Let's see what that simplifies into. 5 on 12. Okay, so there we go. So the probability of x being greater than 4 in our case, for whatever this scenario is, but all we know is that this equation here best estimates the histogram, is 5 over 2. And that's where we're going to leave it for now. There's a couple more exercises, examples that we'll look at in class. Thank you for watching, and see you.